Good evening, everyone. My name is Sai Aditya Pradeep, and I'm the Scientific Program Manager for the AIM for Composites EFRC. Uh, so today is our AIM/Ideas Summer Research and Outreach Program. It's our third webinar of the series and our second hands-on tutorial. The focus of today's webinar is applying physics-informed neural networks to solve partial differential equations, focusing on heat transfer equations in this case. A little bit about this program before I hand it over to Haizo. So the mission of the AIM EFRC is to build an AI-enabled inverse design approach. This is being done in order to fundamentally understand and integrate material manufacturing design of advanced thermoplastic polymer composites. It's also co-sponsored by the IDEAS NSF NRT traineeship. This particular program focuses on training the next generation of STEM students to develop expertise across multiple disciplines, specializing in AI-enabled inverse design, advanced composites, and sustainable manufacturing. This particular series explores the transformative role of neural networks in science and engineering, with a focus on their growing potential to revolutionize data analysis and computational modeling. With that being said, our third webinar will essentially delve into advanced topics, specifically looking at PINNs for solving partial differential equations in heat transfer problems, as an example. A practical tutorial using DeepXDE, which is an open source deep learning library for solving such differential equations, will be included to equip participants with applicable tools and skills. So Nicholas will shortly put the link for all the materials, although he might have already emailed it to you. So he's going to put that in the chat shortly. Before I hand it over to Haizo, I just want to acknowledge the funding for this particular webinar series. So this webinar series is brought to you by the AIM, which is the Artificial Intelligent Manufacturing Paradigm. This is an Energy Frontier Research Center that's funded by the US Department of Energy, specifically the Office of Science, under this particular award number. And we would also like to acknowledge the National Science Foundation Research Traineeship, which is the inverse design training in advanced and sustainable composites under this particular award number. A lot of these webinars occur on a monthly basis, and a lot of this information is available on our social media, whether it's our webpage or our LinkedIn pages. So please do feel free to follow this. A copy of this webinar will be uploaded to our YouTube channel as well, just to let you know. So with that, I think I'll hand it over to our presenter today, Haizo. So Haizo, thank you again for this talk, and looking forward to it.
So welcome everyone to the second hands-on tutorial. So in the first tutorial, we learned the basic algorithm of how weights and biases in FNN are optimized, and how to use a simple FNN to approximate a simple mass function. So today we're gonna dive deeper to learn how to use physical informed neural network, or PINN, to solve a differential equation. So we have emphasized for many times that NN is nothing but a universal approximator. So in the scenarios of a simple mass function, or surrogate NN can be used to approximate the function f of x, which maps input x to the output y. In solving differential equation, what we want is the exact solution of the equation. So this solution could be mathematically considered as a function, which maps independent variables in the equation like x and y and t into dependent variables like u here. Basically, we want to use a surrogate model, surrogate NN, to approximate the mapping solution f of x and y and t. So in addition to that, we also want the NN solution is approximated only using the only exact condition as when we conventionally solve the differential equations. To say we want the NN solution is not data driven, but also driven by the equation itself, and with the boundary condition and the initial conditions. So what we are actually trying to do is solve the differential equation in an alternative way. So our first goal today is to learn the forward PINN with DeepXDE package tool to solve differential equations. We're also gonna start with a very simple ODE problem of a spring vibration. Then we move to a PDE problem of a thermal conduction. After that, we are also gonna learn another powerful tool of PINN, that is the inverse PINN. This tool allows us to discover PDE equation with measured data in an inverse way. So in the first webinar, we have learned the general structure of PIN, and the idea is to incorporate the obedience to the equation as the additional physical laws. And there's an algorithm like the gradient descent to minimize it. The mass essence of the solution, specifically the PDE solution, is a mapping. So we can use a NN to represent the solution of the PDE. And by minimizing the gap between the NN's prediction and the real solution, we would get an approximate NN solution. But since we know the local partial derivatives in every iteration should obey PDE itself, we extract those derivatives during the process and form our new PDE loss. And the algorithm optimizes the new loss together with the original NN loss. So in this way, we impose a physical constraint into our NN model. Therefore, we will have a PINN model. We mentioned before our PINN model is not data driven. When we minimize the original blue loss over here, and we can only borrow the reference value of the boundary condition or the initial conditions. In contrast, when we minimize the red PDE loss over here, we actually don't need any reference values. So the PDE itself is the reference. So the sampling points could be from anywhere within the domain. So it is very important for us to keep this in mind. So for forward PIN, the sample points for two kinds of loss are different, even though they are minimized together. So when we decide to use PIN, we need to know where to sample the training data for two losses. So basically, PIN is approximating the solution of PDE in both directions. The predicted solution should look like the real solution, and the predicted solution should satisfy the PDE itself. Another thing you may wonder is that how those derivatives are calculated in every iteration when we calculate the PDE loss. This process is actually implemented using another special algorithm called automatic differentiation, or AD. It basically works based on the chain rule, which is very basic and important concept in calculus. For example, if we have a simple function like sine of x squared, AD can track specific operation inside of a function like sine and square. So it will give us back the specific derivatives at any x location. So in this specific example, AD gives us back all the derivatives of function of f at x equals 2. So if you replace this simple sine x squared with the entire NN approximation function, basically we can use AD to obtain any derivatives that we need to calculate the PDE loss in every iteration during the NN training. So after understanding the basic math of how individual components of the PINN works, we can say the essence of a forward PINN is a solution mapping approximator guided by the physical equations. So let's begin with our first ODE example. The vibration of elastic spring is a very classic problem. Many applications are based on it, like car suspensions, shock absorbing system in tall building, oscillator inside a mechanical watch. So this vibration motion can be simply described using a second law of Newton in form of a second order ODE. To simply summarize, the acceleration of the object mass is the summation of the damping force, elastic response of spring, and the external driving force. So the solution of the ODE is usually in the form of a periodic sine or cosine function. Thus, this kind of problem is always involved with the vibration and the oscillation. So let's let us first remember how do we solve this kind of problem by math textbook. So we consider it is a second order linear non-homo ODE with constant curves. The solution should be composite with a homogeneous solution and a particular solution. So the idea is to get two solutions separately and combine them together. So we first solve the homogeneous solution by extract the left-hand side of ODE into an algebra equation of an R. And there should be three scenarios. One is two different real numbers, another is two identical real numbers. And we have here the third one in this specific case, which is two imaginary numbers. So our homogeneous solution in the form of the sine and the cosine. Then we assume a particular solution with undetermined constant and substitute it back to the ODE and determine the constant A and B. And finally, we would combine two solutions together, and with the initial condition, we would get our final solution. So the conventional solving mindset will definitely solve this simple problem for us. But what if some of the term inside the ODE get really complicated? To say, if we have a very complicated driving force like a discontinuous puzzle or chaotic like high frequency driving, the solving process will be very hard. And things will be really tricky if some nonlinear factor appear in our ODE. To say some of the constant become a relevant function of a time or space. So we need something universal to help us to do the job. So we're still using the time-specific problem of this ODE with two initial conditions, which indicates the initial displacement of the spring is 1 and the initial velocity is 0. Since our goal is to find the response x of t solution, the NN's mission is to approximate the mapping from time t to displacement x. Through optimization, the optimal weights and biases that make the minimal combined loss will be found. For this red loss over here, AD gave specific the first order derivative and second order derivative values to calculate the ODE loss. For the blue loss over here, as we point out for many times, the training samples are only from the knowing reference, which are just two initial conditions over here. Since this is a 1D problem, so the blues on the initial condition is essentially the misalignment on displacement and velocity at the initial time. So our expected solution should match both initial condition and the ODE itself. Just like the last time, we still use the Google Colab to run the codes. So the instructions are pretty similar, except we need to install the DeepXDE manually on that platform. Because our forward PINN code today is performed on that specific package, one thing you need to know is that the DeepXDE is not the only way to implement a PINN structure. For beginners who just wanted to use the function of PINN to solve some tricky ODEs or PDEs, it is surely a good tool. All you need to do is just learn how to put the right argumentations inside the functions. However, I think since we have learned everything fundamental about the PINN structure, it wouldn't be very hard to establish a PINN by ourselves. So one good thing about the building the NN ourselves is that we can fully customize the functions, training strategy, and specific training frameworks like TensorFlow, PyTorch, and JAX. But still, we will learn how to implement NN on DeepXDE first in this tutorial. So upload the Spring Vibration notebook file to the content folder, then open up the terminal panel in the button, and type in the pipestall DeepXDE to install the DeepXDE package. You should once it's finished, you should see a successful notice on there. Then copy the code from Spring Vibration to our online notebook. From the first slide, import DeepXDE to the last slide, POT show. then click the run button, you should see some output coming out. And when the approximation is finished, there will be a result graph which shows the response x of the x of t curve, and that is the solution of the ODE that we want. So the coding structure of this Python notebook is very similar to one of the to the first tutorial. So the first part is to import the necessary package that we need, fix the randomization, and check the package version alignment. Since we are solving an ODE, we need to define the ODE first. We need to use the geometry function to create a 1D time domain that range from 0 to 10. Then use diff function to define the equation using graph function inside the DeepXDE, and the first order corresponds to Jacobian subfunction, and the second order corresponds to the Hertzian subfunction. The U and T are the displacement and time over here. Then the index argumentation is to let function know which derivative that you want to define. So here I equals 0 means the first derivation that you want to do on T, and J equals 0 means the second derivation that you still want to do on T as well. So initial displacement condition is defined by IC function in DeepXDE, and we still use the Jacobian to define initial velocity condition. Then we insert the ODE and the geometry into the solver. We take 200 samples for ODE loss and only 2 samples for NN loss, because we only have 2 initial conditions. So and we take another 1,000 points for testing. The NN structure is set with 3 hidden layers, each with 50 neurons. Learning rate is 0.01, and total learning iteration are 20,000 epochs. So in the output, the right 3 columns are the loss of ODE and the 2 initial conditions. The left 3 are corresponding test errors. Just like the last time, we use FNN to approximate simple function. So both training loss and test error are gradually reduced through iterations. The training time would not be very long. For 20,000 epochs, it should be 1 or 2 minutes. So after the first simple ODE problem, we consider a PDE with more independent variables. A simple and canonical example is the Laplace equation. It is widely used in studying mass diffusion or heat conduction. The Laplace equation is one of the simplest version of energy equation, which is one of the 3 classic equations in mechanics. So those 3 equations are mass equation, momentum or NS equation, and energy equation. They represent and originate from the 3 basic principles of physics, which is conservation of mass, conservation of momentum, and conservation of energy. So Laplace equation here of the temperature is a simple variant of the energy equation. The equation only considers a temperature change along the spatial dimensions and no changes on the time axis. Therefore, this is a very canonical equation that studies the steady state. So in our demo problem, we assume we have a square 2D square domain, and the material inside is homogeneous and anisotropic in thermal properties. And there is also no internal heat generation, and we consider only the steady state. So if we further consider a very simple BC configuration where there are 1 hot boundary and 3 cold boundaries, the problem can be reduced into a non-dimension form like this. What we need to do is solve this PDE with 4 boundary conditions. So conventionally, we know from the math textbook, we can solve this PDE by separation of variables, which is one of the classic way to deal with differential equation look like this. So first, we assume the temperature solution T of x and y is a multiplication of 2 separate functions, big X of x and big Y of y. This is the key idea of separation in the method name. So, and we substitute this assume formula back and change the form a little bit into a fraction form with some eigenvalue lambda. Here is the result of the fraction result. Then we would have two degraded ODEs. So through separation of variables, we basically have degraded two variable PDE into two ODEs. That's the whole text become easier. Then we first solve the ODE for the solution big O x of s and get a solution in the form of a sine series. Then we move to solve for big Y of y. And we put them together, we would get an analytical solution in form of a Fourier-like series. If we take like 50 even terms, which is n equals 100 for approximate solution, the solution temperature should look like this. You can say how the temperature varies from the top hot boundary to other three cold boundaries in this small 2D space. So that problem we just solved with separation of variables use a very simple BC configuration. But what if we use more complicated BCs? Even though we just change the boundary condition a little bit to say we let four boundaries in four different temperatures, the conventional separation of variable would fail. So we may need an alternative way to do the job. So back to our way of PINN, we simplify this problem of a Laplace equation with four different BCs. Similar to the previous ODE, the NN's mission is to approximate the solution mapping from X, Y to temperature D. So the inputs of NN are X and Y, and the output is T. The blue loss part is trained by samples from four BCs. This time, since we are studying on a 2D problem, the samples from BCs are theoretically infinite. So it is not like the last ODE example where we only have two samples from two initial conditions. Then the red loss is calculated by ADE, and the training samples are from anywhere within this small square domain. So everything would basically like what we do for solving that ODE, except that we have two inputs instead of one. So the coding part is basically the same as the previous ODE case. We upload the code file to the content folders and install the DeepXDE package. Then we are doing the exactly the same step, like copy the code from 2D plays 2D play steady notebook to our notebook that we just created. Then we just keep the preset parameters and run the code. We would have the outcome. You would see a resultant graph showing the steady temperature field in the square domain. Since our setup values for temperature on 4BCs is evening spacing, so we can say the showing color distribution will be symmetric along the diagonal line. So the base structure of PDE code is the same as the ODE code. We use the function Herschen to define the second order derivatives and use geometry to create a 2D square domain. Then define four BCs with four different temperature values. In approximator setup, we inject the PDE and the BCs takes 1,000 example within the whole 2D domains for training of PDE loss, 400 samples for BCs for NN loss, and we take another 1,000 sample within domain for testing. Then we set up the NN structure and learning rate and training epochs number and then initialize the approximation. So the output is divided into loss and error parts as well. So if the approximation is good, you should see the overall temperature domain is something like this. The top and the left parts are in low temperature profile, and the bottom and the right parts are in high temperature profile. And the training time for 10,000 epochs should be around 3 minutes. So the running times of forward PINN with DeepXDE is quite fast, even if it's run on the Google Colab. So we have used one ODE example and PDE example to show you how forward PINN solve differential equations. Another powerful feature of the PINN that a conventional method will not have is to solve the inverse problem. So based on the last equation, if we consider a transient state, that means we take the dimension of time into our consideration. We would have a heat conduction of the 2D problem looks like this. The temporal term is associated with the special terms with thermal diffusivity, which is purely dependent on the material properties. Try to imagine a scenario when we invented some new material and we don't know what would the thermal performance of this new material be. If the material is still homogeneous and isentropic, it would still obey the heat conduction equation, but the thermal diffusivity is undetermined. So in an inverse problem, we have the knowing field data and or to say we have the measured data. We need to inversely find the correct material properties for this material. So the base structure of inverse PINN makes no difference to the original forward PINN. In the forward PINN, we are actually solving for field solution. So the reference data for blue NN is only from BCs, which can be seen as an insufficient data set. That's why the forward PINN what we need to do is just to inform the NN. So the knowing PDE is sort of provide information for the training process. If we think in another way, we have enough data. When we have enough data samples, we just want to approximate the mapping from x, y, and time t to temperature t. This process would have no difference with what we do in the first tutorial. We just approximate a simple function by optimizing the width and biases to minimize the blue loss over here. Therefore, there is no need to impose a physical constraint. Thus, we don't need to know the exact form of the PDE. This is exactly the same situation we will have when we face an inverse problem. So in contrast to a forward PINN, where PDE provides helps to NN, in inverse PINN, NN would provide helps to PDE. Instead of optimizing the only weights and biases of NN to minimize the loss, in inverse PINN, we say those unknown coefficients in PDE, just like the alpha over here in the heat conduction equation, as an trainable parameter, just like weights and biases. And there's an algorithm to optimize them together with in this training process. So this is the key difference between forward PINN and inverse PINN. So to summarize a little bit, the mission of the forward PINN is to solve an undetermined PDE with partial or insufficient reference data on BCs or ICs. The idea is to let PDE to provide additional information for NN for better approximation. In contrast, the mission of an inverse PINN is to inversely find the undetermined PDE in a data-driven way. The idea is to optimize the undetermined coefficient in the PDE along with weights and biases with sufficient data from all domain. So back to our coding part. I originally planned to show this demo code also with DeepXDE package, but there's an issue of a version alignment in using inverse function or PINN with the Colab. So here I just using the code written by myself to give you the demo. The key structure of the code is the same. So we still upload the 3 files, including a notebook file and a Python file and MP3 data files to the online content folder, and copy those codes inside the notebook and and use the default setup. I click the run button, you should see some output coming out. So the dataset I use here is a solution result of this specific heat conduction equation, and the coefficient is around is exactly 0.1. So if you check the output history of the target coefficient K, which is supposed to be 0.1, you can say the prediction of this coefficient is gradually approaching the right value. This means the inverse PINN has captured the right PDE. And the training time of this specific inverse problem is longer, since the inverse problem test is usually more complicated than a forward one. So here, if consider a more complex inverse problem, think about there is a new material, like we have their idea about the thermal performance of this material, including the PDE foam. It could be anisotropic on heat conduction in terms of X and Y direction. That means there will be multiple undetermined coefficient to optimize. So their idea means we are blindly guessing the form of PDE. So we put every possible terms into the PDE and let PDE pick the most effective ones. So the algorithm needs to approximate the multiple coefficients at once to minimize the total loss. So for the coding part, just like what we did for the first example, just upload and copy everything in the second inverse problem folder. And the dataset is the same, and the right coefficient on the both spatial direction is the same of 0.1, but you can say in the output the NN is actually approximating 4 coefficient for or 4 terms. And in the output history, the coefficient of 2 second order terms are approaching the correct value of 0.1, and 2 non-effective terms are given with a very small coefficients. This means the inverse PIN thinks these 2 terms are less effective than the former 2. And we know the second inverse problem is naturally more complicated than the first one, since there are more uncertainty that the PIN need to fix. Therefore, you can say the training epochs number are higher and the training strategy adopts two stages of learning rates. So the definition of the undetermined coefficient or PDE is inside the inverse PIN model. We set the undetermined coefficients as the trainable parameters, just like the width and biases, and add the coefficients into the PDE. The exact procedure is in the second problem as well, except that there are more coefficients that is defined and added to the PDE. So those are like all the content for the second tutorial. We introduce the forward PNN to solve a simple ODE and the PDE, and we also introduce the inverse PIN for inverse problem. So everyone can try the demo code for 4 examples on Colab by yourself. And if you have any question, please feel free to ask in the chat box or QA of the room. And I would like log into my own Colab to give you a quick and simple demo. So just like the last time, we create a new notebook on the Colab, and we upload those code under this content folder. And here we in the online terminal, we just install DeepXDE. And when the installation is complete, you should say there is a successful notice. And we copy the major code from notebook that we just uploaded to this content folder. And we hit the run button, and there will be some results coming out. And for this simple spring vibration case, this should be coming out less than 1 minute. And for the second PDE, we're still doing the same process. We copy the code to the notebook, and when the first one is finished, we run the second one. You can say the total epoch size set over here is 20,000 epochs, and it's already 70,000 and about to finish. So when it's finished, you can say this is a response curve of the spring vibration, and we run the second one. So basically, when you just follow this instruction to run the code, you should get some output. You can try to adjust the learning rate and the engine structure over here to see the difference. Okay, that's basically everything I want to share today. If you have any questions, please type in the chat box or the QA session in this room meeting. What are the limitations? Okay, so I think the first limitation that will be PINN is quite sensitive to noise. So if your data like for inverse PINN, it is very sensitive because for in the inverse PINN process is the whole process is actually data driven. So if you give the wrong data to the PINN, you won't give a very accurate result. And I think another limitation is that the misalignment between the equation itself and the simulation data, because sometimes like from real experiment, there's always like small noisy terms inside of the governing equation, but sometimes we just don't know what that is. So the data we provide for PINN usually contain those terms, but the equation that we gave to the PINN don't contain those terms. So there will be some misalignment, which will lead to bad performance of PINN.
I think we have
Yes,
another one as well.
yeah. Of course, we can solve the couple equations. So you can just insert how many equation, how many partial equation that you like into the code. So let me show you this one. So inside this code, you can see for our NN model, there is only one equation. But if you want to solve a couple equation, you can just insert all of this equation together and add all the loss function of the loss, and that's going to minimize it. I think it's still. I think the current challenge is still between the noise data and between the data and the equations, because there's always noise and disturbing term inside our simulation. So there will be definitely problems, and people trying to use an alternative way like a Bayesian neural network to use certainty strategy to solve this problem. I think PINN is not limited to this tool. I mean the whole concept and the whole idea of PINN is very important. So when we like build our own NN model, we should always find something like governing or some constant to provide additional information for our NN instead of just let it purely data driven.
Any other questions from the participants?
So we
I think you,
say the second PDE case is coming out. So it's approximately 3 minutes. And you should say a temperature field looks like this.
I think there's one more
How about
question from Ali.
multi-scale?
Yeah,
Yeah,
yeah.
I see that.
Okay. Multi-physics problems. How about multi-scale or multi-physics
Um,
problems?
so for problems in the micro scales, we use a continuum way to understand problems. So that's why we invent all kind of a governing equation. For I think for like micro scale or meso scale problems, when you dive into scale of an atom or cellular level, I think those like governing equation may not be the rule over here. So I think for those things, you can just trying to depends on the problem you want to solve. You can just try to use first use the classic data driven mindset to solve it, and try to find some constant during this process. For instance, like energy conservation, does your problem has this kind of a constant laws into it, and trying to modify those constant laws into the constraint that can provide additional information for NN.
Yeah. Thanks, Haizo. I think you answered Ali's questions.
Yeah.
There any other questions, please feel free to put it in the chat box. Aizo, is there anything else you would like to add?
Yeah.
I think we are in the final few minutes of the webinar anyway. Yeah. Okay. If if there are no other questions, then I think we can possibly conclude the webinar if that's the case. So, as mentioned before, the recording will definitely be made available. Yeah, I think thank you for the acknowledgement again, Haizo. So definitely want to
Yeah.
acknowledge our sponsors. If you do have any questions, you can feel free to reach out to either Haizo, Nick, or myself. Um, The effort is to try to have these webinars on a recurring basis, although this three-part series is focused as a outreach webinar series over the summer. So please be on the lookout for more such webinars. And if you have any suggestions, I'm hoping you guys all filled out the survey. If not, you can let us know as well anonymously. But we are looking to improve a lot of these offerings in the months to come. So any of your suggestions are very welcome. And then to end, I definitely want to thank our host, Haizo, as well as Nick for organizing this series. I think some of this was also cast onto LinkedIn Live, so I think a certain version of this might also reside over there. So thank you, both of you, for this effort, and definitely want to thank our participants. I think a lot of the feedback that was given over the course of the webinars, we did try our best to incorporate it. And we all hope you enjoyed it and more importantly, learned something from it. So thank you once again, everyone. Yeah.